Hello everyone, my name is Francesco Tamagnini and today we will talk about the renal system. This is our second lecture and we will focus on the homeostasis of electrolytes and water. So if I'm going to be doing a good job, you will be able to understand by the end of the lecture that the elaboration of urine depends, of course, on the anatomy and the properties of the different parts of the tubular system of the kidneys. You will understand how the epithelial cells which line the lumen of the tubular system control the absorptive and secretory properties of the tubule and of the kidney function. You will understand how the regulation of sodium and potassium excretion is in the kidney is responsible for the balance of these two ions in the body and how this process is controlled by hormones. You will also understand how the kidney can produce concentrated urine, and that the concentration of urine can vary as a function and as a consequence of the regulation of water balance by generating an osmotic gradient and a countercurrent multiplication. While in the collecting duct, the hormonal regulation of water reabsorption allows to concentrate or dilute the urine depending on whether or not we want to concentrate or dilute the content of the body fluid. So first of all, we will talk about how urine is elaborated, and we will talk about the function of the different regions of the nephron. We will then focus on the regulation of the sodium and potassium balance, and that will be the second lecture. And then finally, the second part of the second lecture. And then finally, we will talk about the regulation of the water balance. That will be the third part of the second lecture. And we will focus on the formation of the osmotic gradient by countercurrent multiplication. And finally, how the antidiuretic hormone, or ADH, regulates the formation of weak or concentrated urine in the collecting duct. Okay, so as I concluded last time, after the plasma is filtered through the glomerulus in the Bowman capsule, the filtrate gets conveyed into the proximal convoluted tubule. In the proximal convoluted tubule, we have two processes which are obligatory reabsorption of all filtered glucose, amino acids, sodium, chloride, and bicarbonate. Okay? So in the proximal convoluted tubule, we have obligatory reabsorption of all filtered glucose, amino acids, sodium, chloride, and bicarbonate. Okay? So the semi-processed urine, gets then conveyed into the loop of Henle. In the loop of Henle, there will be an osmotic gradient created by sodium chloride reabsorption into the interstitial fluid, while the tight junction prevents the water movement. Okay, so sodium chloride will be moved into the interstitial fluid, but the tight junctions will prevent the movement of water. Okay, so this is very important, but we will go through this in more detail later on. This is just to have an overview. Almost finally, in the distal convoluted tubule, we have regulated absorption and secretion of various ions and compounds. And then finally, in the collecting duct, we do have the final regulation of the concentration of the urine by the antidiuretic hormone, So the antidiuretic hormone is released if the osmolarity of the body fluids is more than 290 milliosmoles per liter in order to regulate water loss. Okay, so if the osmolarity of the body fluids goes above critical value of 290 milliosmoles per liter, then the loss of water via urine is countered by antidiuretic hormone. And once again, we will go through this in detail. This is just to give you an overview. Okay, so now let's talk about tubular specialization. Okay, so the processes of reabsorption and secretion depend by many factors. So the first factor is the leakiness of the junction between tubular epithelial cells. Okay, so tubular epithelial cells form a wall like any epithelium, from the skin to any epithelium that covers the body. So the junctions between epithelial cells can be loose and let water flow through adjacent cells, or they can be tight, okay? And tight junctions are less permeable to the movement of substances, including water. So tight junctions are less permeable, and moving from the proximal to the distal tubule, the junction between cells becomes more tight. So in the proximal tubule, the junction between cells will be more loose, allowing the passage of more water. And then the more we move towards the distal tubule, the tighter the junction between cells becomes. Second factor, the epithelial cells express carriers, okay? Protein carriers of the plasma membrane. So we talked about this in certain detail when we were talking about the transport through and around the cell. These can be membrane channels, they can be pumps, and they can be either positioned in the apical membrane. So the apical membrane is the part of the plasma membrane of the epithelium which is directed towards the lumen of the tubule, while the basolateral membrane is the part of the membrane that is directed towards the interstitial space, the interstitial fluid, in this case on the right hand side, and hence towards the blood, towards the inside of the body, or towards the neighboring cells. Okay, basolateral is the base and the sides of the cell. So I hope you see my marker here. So this will be the apical membrane, while this one will be the basolateral membrane. Okay, so I'm going to make the apical membrane blue, the one that goes towards the lumen, while the let's make it purple. The basolateral membrane is this one here. Okay, so as you can see, the composition of the carriers in the apical membrane and in the basolateral membrane is different, and we will see soon why. Okay, let's talk now about the proximal tubule. In the proximal tubule, we do have important processes of obligatory reabsorption, okay? And most of this reabsorption of substances from the tubular fluid into the blood is driven, almost all of it, by the movement of sodium, glucose and amino acid reabsorption into the blood occurs via facilitated diffusion. So amino acids and glucose just follow their gradient of concentration, moving through carriers on the plasma membrane. But the energy for this movement is solely provided by the concentration gradient of glucose and amino acid. We also do have processes of secretion, so from the blood into the tubular space. And this is the case, for example, of organic acids. Do you remember the para-aminohypurate? And many drugs, such as penicillin, and many other substances which are biotransformed by the liver and excreted via the kidneys. So, as I mentioned, sodium and bicarbonate are fully reabsorbed in the proximal convoluted tubule. And of course, as they are reabsorbed, there is a slight drop in the osmolarity of the filtrate. So since there is this drop in the osmolarity, and since the junctions between cells in the proximal convoluted tubule are not very tight, there is an osmotic equivalent amount of water that moves from the proximal convoluted tubule into the interstitial fluid. Okay? So in the proximal convoluted tubule, we do have mostly, four characteristics. The first one, as I mentioned, but as I said, I will repeat the concepts that are important. We do have leaky tight junctions, okay, between epithelial cells. These junctions are actually so leaky that allow the passage of water, but not only water, even potassium, okay? So when potassium moves across the epithelium of the lumen by passing between cells, this kind of reabsorption or movement between cells is paracellular, okay, between cells. Sodium, once again, move down its concentration gradient, so from the lumen into the interstitial fluid. But this process in time would, somehow be limited, right? In the sense that if you only are driven by the gradient of sodium, at some point, sodium will reach its electrochemical equilibrium. So in order to keep sodium being reabsorbed via sodium permeable channels on the apical membrane of the proximal tubule epithelium, there is a sodium-potassium pump in the basal membrane of the proximal tubule epithelium, which keeps generating an electrical and chemical gradient of sodium by pumping 2 ions of sodium into the interstitial fluid and 2 ions of potassium into the cytoplasm of the epithelium. Okay, so by keep pushing it sodium out of the cell into the interstitial fluid, that will keep intact the chemical and electrical, the electrochemical gradient of sodium that will allow sodium to passively diffuse from the lumen into the cytoplasm and from the cytoplasm of the epithelial cell into the interstitial fluid. Okay. As I said, glucose and amino acids are 100% reabsorbed, and this is mediated by sodium cotransporters. So the energy for the movement of glucose and amino acid is provided by the sodium gradient. While bicarbonate moves into the interstitial fluid via bicarbonate chloride exchange. So ultimately, the movement of glucose, amino acids, and sodium is kept on going by the polarity of the position of the ATP sodium pump on the basal membrane of epithelial cells in the proximal convoluted tubule, which keeps intact the sodium electrochemical gradient, which allows the movement of sodium from the lumen into the interstitial fluid. And because of the symporter of sodium glucose and sodium amino acids, allows the reabsorption of glucose and amino acid in the proximal convoluted tubule. while bicarbonate moves into the interstitial fluid following bicarbonate chloride exchange. So the key features of the proximal convoluted tubule is that it is highly permeable to water and solutes because of the leaky tight junctions, and around 66% of ions and water are reabsorbed into the proximal convoluted tubule. Okay. So the second step, the second part of the tubular system of the nephron we will talk about is the loop of Henle. So as we mentioned last week, there are two types of nephrons. Cortical nephrons, which represent around 75% of the overall nephrons, and the juxtamedullary nephrons, which represent around 25% of all the nephrons. Water is the water that is not reabsorbed in the proximal convoluted tubule so the water that is reabsorbed in the loop of Henle is mostly reabsorbed in the descending loop. Okay, the descending limb of the loop. Sorry, there is a typo here. The water is reabsorbed in the descending limb of the loop of Henle, while the sodium chloride is reabsorbed in the ascending limb of the loop of Henle. Let's look at it in more detail. So in the ascending loop of Henle, we have tight junctions which do not allow the movement of water, or at least the permeability to water is reduced through the tight junctions. Sodium and potassium are co-transported with two chlorides from the lumen into the cytoplasm of the epithelial cell of the ascending loop of Henle. And the energy for this process is provided by the gradient of sodium generated by the basal ATP syntase. Okay, so ATPasic sodium potassium pump, because this pump keeps on pumping sodium into the interstitial fluid, generating an overall electrochemical gradient of sodium, which is directed from the lumen into the interstitial fluid. So the movement of sodium, potassium, and chloride outside of the lumen in the ascending loop of Henle generates results into the hypotonicity, reduced tonicity, reduced osmolarity of the filtrate, around 100 milliosmoles per liter. Okay, so this is called the diluting segment. While of course the interstitial fluid will become hypertonic. Okay. The transluminal potential is caused by the back leak of potassium, which then in turn drives the movement of calcium and magnesium through the time. So the movement of sodium and potassium and chloride through these transporters, driven by the ATP sodium potassium pump, will leave the lumen osmolarity low, will increase the interstitial fluid osmolarity, but then the presence of leak channel 2 potassium on the apical membrane will result into the back leak of potassium into the lumen. So the back leak of these positive charges into the lumen will allow calcium and magnesium to diffuse into the interstitial fluid via the tight junctions. And the movement of these ions will generate a transluminal potential which is comprised between 6 and 25 millivolts. The key features of the ascending loop of Henle is that it's highly permeable to solutes, especially sodium and chloride, but not water. Okay? So this is very important. More or less 20% of ions and water are reabsorbed into the ascending loop Henle. We will go back to the loop of Henle. Okay, we will look in more detail at the role of the descending limb and ascending limb in generating an osmotic gradient with countercurrents for the regulation of water. But we will see these in the later part. Okay, this is just to give you an overview, but we will go into more detail. Okay, step 4, the distal tubule. So in the distal tubule, we do have regulated absorption and secretion. Okay, so if in the proximal convoluted tubule the reabsorption was obligatory, and also secretion was obligatory, in this region is regulated by enzymes such as renin and aldosterone. Okay? Renin is an enzyme, but with a strong hormonal nature, yeah, because renin triggers a cascade of signaling. So let's look at it in more detail. So the epithelial cells in the distal convoluted tubule are called principal cells, and they secrete potassium and they reabsorb sodium. And this is due mostly to the action of aldosterone. Okay, so the reabsorption of sodium is, as usually, driven by the sodium-potassium ATPase pump, but the movement of potassium is mostly driven and caused by the movement of sodium. Okay, so the amount of sodium that is reabsorbed, and hence the amount of potassium which moves back into the lumen, determines how much potassium is lost in urine. And this is once again dependent on aldosterone. Okay, don't worry if you don't understand these too much. We will go into more detail. Okay, just remember that the key features of the distal convoluted tubule is that it is permeable to solids such as sodium and potassium, but the permeability to these and the movement of these ions is regulated by hormones such as aldosterone and enzymes with signaling functions such as renin. Okay, this is the key message that in this instant you have to take home. We will go back to the fine mechanisms of regulation of potassium and sodium excretion.